Hi judges, my name is Atharv Pratap Singh Chauhan and this is my submission for the IICPC Summer Trading Hackathon. I competed solo for this project and my goal was to build a highly deterministic institutional grade benchmarking sandbox for HFT engines. Most standard benchmarking tools rely on heavy web protocols like HTTP and JSON parsing, which introduces massive latency spikes. Standard server also use a thread per connection model, which causes the OS scheduler to collapse under a microburst of orders. To fix this, I abandoned standard web paradigm entirely and dropped down to raw TCP sockets, custom binary protocols, and strict hardware level CPU isolation. Let's look at the systems live. Now, opening the VS Code and going to the terminal, entering the command docker compose build and running it. The entire ecosystem is fully decoupled into separate microservices and orchestrated via Docker Compose. As you can see these services spinning up here. The API gateway is written in the fast API, the live dashboards run on NGINX, and the sandbox run in the isolated Ubuntu container. To guarantee that we are measuring the contestant pure algorithmic efficiency and not background OS noise, the sandbox container uses cgroups to strictly pin the engine to CPU core 0 using the cpuset flag. This preserves absolute L1 and L2 cache locality and eliminates context switching. We also hard kept the memory at 512 MB to enforce strict algorithmic space complexity. Now opening my web browser and navigating to the fast API Swagger UI, refreshing the page once. Now opening the upload engine menu, try it out, choose file. I already made one file, matching engine.cpp. I'm uploading that, execute. Now it's showing loading. Now, this is the control panel ingestion pipeline. A contestant simply uploads their raw C++ limits order book file through OpenAI gateway. Behind the scenes, the fast API hub intercepts the file, talks directly to the host Docker daemon via mounted Unix socket, and triggers a dynamic compilation inside the infrastructure layer using G++ with the full O3 optimizations. The sandbox container instantly boots up on the port 9000 fully armed and waiting for the market simulation. Now navigating to the VS Code again. Opening one more terminal. Now navigating towards the load generator file. So cd load generator. Now launching the attack. Sorry. Now we simulate peak market volatility by unleashing the load generator. I am running the C++ attack right now. Instead of spawning thousands of heavy threads, it uses a single threaded asynchronous kqueue event loop to handle 200 concurrent non-blocking TCP connections simultaneously. It just blasted 5000 orders into the sandbox in milliseconds. If we look at live engine telemetry dashboard, the performance lines are incredibly stable and flat. A P50 median latency is sitting around 2.36 milliseconds, and the absolute worst case of P99 tail latency is tightly bound around 30 milliseconds. We achieved this tail latency by doing two things. First, we engineered a custom 29-byte packed binary memory struct, allowing the sandbox to cast raw byte straight out of the socket buffer with zero decelerization overhead. Second, we explicitly applied the TCP node play socket option at the kernel layer, completely disabling Nagel's algorithm to ensure unbuffered packet transmission. Now, the fact that a P99 latency is so tightly grouped with our median latency proves that we successfully eliminated OS thread jams, network buffering, and hypervisor jitter. The system processed the entire load statefully across the virtualized hypervisor bridge network without dropping a single packet. The entire architecture, completely with detailed documentation in the README file, and the full system design blueprints is fully public on my GitHub repository. Thank you so much to the IICPC team for organizing a fantastic and technically challenging hackathon. Let me know what you think. Thank you.